Super excited to be here. Today, we're going to be talking about building Ekko. And Ekko is a real-time message processing framework. And we're going to dig into exactly what that means. And just a quick intro. My name is Will, and I'm here with Drew and Alex today. Unfortunately, Dory wasn't able to make it. But as you can see, we are spread out all over the world. And it was super fun to try to learn how to collaborate remotely, which is something pretty much the whole world has tried to figure out over the last year and a half or so. But yeah. And just a quick teaser. This is a super simple chat application, and it's just to show kind of a contrived example of something you could build with Ekko, and all of the real-time capabilities are built on top of Ekko in this example. And something unique you might notice is that on the Angry channel, all of the actual text messages being sent back and forth are being transformed. And so that's one of the key things we're going to be talking about later. Just a quick overview. We're going to be talking about real-time web applications, what exactly we mean by that, also why they often need dedicated real-time infrastructure, and then also why they often need real-time middleware and what exactly that is. That's kind of not a super common phrase. After that, we'll introduce Ekko, and then we'll go over some of the engineering challenges we faced, and then we'll wrap up with some resources in case you want to learn more about Ekko and jump in, since it is all open source. So first off, let's talk about real-time web applications. So real-time web applications are literally everywhere. They're the live dashboards we see. They're all the apps that show you the driver location or the package location on a map. And then there are also all of the chat features and everything. These are just a couple examples, but the whole real-time feature or real-time features are pretty much everywhere now. When it comes to trying to define and classify real-time web applications, it really all boils down to the user's perception. And this is a quote that I think sums it up pretty well. And it says, a real-time interaction has a human angle because one of the collaborators in any real-time data exchange is always a human. Hence, the human perception of a real-time event is very important. And this is kind of a weird, odd definition, but really it's just saying that real-time in terms of web applications is completely focused on just trying to make things happen as quickly as possible. And so really the only metric that matters is the human perception. And this kind of leads to some interesting insights. So the first one being that we have to shift our idea of how we think about data being transferred. And so going back to kind of a traditional HTTP request response cycle, this is centered on the idea of pulling data, where you have data that accumulates somewhere, usually in a database, and then a client can make an explicit request for the data, and then a server can respond with the data. And nothing actually happens until that request is made, which is why it's called pulling data. The client is pulling data to itself. And this is just to be distinct from the data push pattern. And so in the data push pattern, you usually do start off with a similar request where the client is requesting data. But the difference is that it's requesting that new data be sent over as soon as it's generated. So in a data push pattern, as soon as the data is available, it's pushed to the client. And if you think about real-time web applications, pretty much everything follows this data push pattern. Otherwise, you'd have to refresh your page to see if there's new chat messages, and that'd be a really poor user experience. Another interesting pattern that kind of arises when talking about real-time web applications is a shift away from the kind of server-client model and a movement or a shift towards the idea of publishers and subscribers. And so the key difference here is that now we're not talking so much about the actual underlying hardware that's being used. And instead we're talking about the roles that the different devices are being used for. And so on the left, we have a single publisher, and it's sending messages to the subscriber on the right. And just a quick clarification also, in real-time messaging or in real-time web applications, we use the term message for pretty much any data being sent. It could be actual text messages, but it could be just any bits of data. So it could be geolocation data or any of those things. But again, you calling it a message is once again kind of operating at a little bit higher layer of abstraction instead of talking about the actual implementation details. And expanding on this idea of pub-sub messaging patterns, you can also have one-to-many. So we have a single publisher publishing to 3 subscribers on the right. And then you could take this even further and do many-to-many, And this, it looks a little crazy. This is actually totally possible. This is basically like a peer-to-peer network, and something like WebRTC totally supports this in real time. This actually isn't the most common for most web applications. Most web applications are centralized. And so what's more common is to actually have kind of a central hub to manage real-time connections. And so in this example, we have a central hub that all the devices are connected to. And then so a publisher sends a message to the pub or to the hub, and then that emits it to all the subscribers. And then last but not least, so far we've only been talking about devices as being a publisher or a subscriber, but it's actually very common to have devices be both publishers and subscribers. And if you think about, again, like a chat example or something, anytime you send a message, you're a publisher. Anytime you receive a message, you're a subscriber. And then so in this example, we could see that any device can publish to that pub sub hub, and it gets emitted to all relevant subscribers. And this kind of big level picture of pub sub messaging, which is pretty common in the real-time web application space. Now, we talked about why having a central hub is helpful for just keeping things simpler, especially if you already have kind of a centralized web application. So a hub makes sense, but the next question then that follows is, how do you actually implement this if you want to build one yourself or start implementing real-time features? And so it kind of makes sense to start off by talking about the actual communication protocols, since with real-time features, it's all about sending data very quickly. So communication protocols kind of make sense. And if you start searching around for like real-time communication protocols, you're going to run into a lot of these different types of things. So there's a bunch of HTTP derivatives, such as server-sent events, long polling, and HTTP streaming. There's WebRTC, which is that peer-to-peer protocol we talked about. And then there's also web transport and WebSockets. And so all of them have different trade-offs. And so when we go through them, it kind of makes sense to compare them. And so the first thing, they all need data push, because we established that's pretty essential for real-time messages, and they all do support that. But the next thing is, if you want to support bidirectional communication, where devices can be both publishers and subscribers, that kind of rules out the HTTP derivatives. Some of them, there are some hacks and workarounds to do bidirectional, but it's not really the standard use case for them. Next up, if you're adding a feature to a web application that's already a centralized web application where it's hosted on a server somewhere, it makes sense to follow the same pattern versus trying to set up a whole peer-to-peer network for the real-time feature. And so that kind of rules out WebRTC for most applications, just because that add a lot of unneeded complexity. And last but not least, you want something proven in production most likely, and so that rules out web transport, which is super interesting, but it still is an emerging technology, so it's not as battle tested as the other ones out there. And that leaves you with WebSockets, which should make sense. WebSockets is definitely the most common way to implement real-time features in web applications. And so let's say you actually are going to jump in and add a real-time feature. And so it's actually surprisingly easy to get up and running. You just open up your application code. You can add a WebSocket library such as Socket.io. That's pretty much it. Like, you could get a demo up and running in an afternoon pretty easily. Now, the complexity or the challenges happen when you actually want to deploy this into production and you want it to be a robust, scalable solution. And so you're going to run into a lot of different challenges. So some of the challenges are if you're adding multiple real-time features, so things like chat boxes and then like location data and dashboards, and they're all different real-time data, and managing a bunch of different types can be very challenging. Also, if you have to horizontally scale your application, managing real-time connections and data across different servers can be very, very challenging. And then also, a lot of times real-time features scale or have different scaling needs than the actual application that they're integrated with. And then so building things that are able to accommodate both can be challenging, since they fluctuate at different times. And so because all of these different challenges are very common and arise pretty quickly with real-time features, it's often a good idea to actually have dedicated infrastructure specifically for your real-time features. And that's actually what these three companies do. So these are some of the leading companies out there that provide real-time infrastructure as a service. And this is great for like anyone who doesn't want to build things from the ground up and want to get up and running very quickly and have a lot of guarantees and reliability. These services are amazing at that. And they all pretty much advocate the same idea. They all advocate the idea of decoupling your real-time infrastructure from your application. Now, if you start digging into this even further and start actually implementing different tools and features that are real-time, you'll probably run into another kind of need or pain point sooner or later. And that's the need for real-time middleware. And the idea behind real-time middleware is just the idea of wanting to do some sort of business logic on the actual data, the real-time data in transit. And then so examples of that. So for instance, when you open up the Uber app, it doesn't show you every driver in the world. It just shows you the ones that are right around your area. So there's some filtering going on. And then similarly, a very literal filtering going on is with chat messages, like in-game chat and whatnot, they often filter out profanity. So again, you have messages going between different users, but somewhere in the middle, some business logic is being applied and profanity or anything offensive is being filtered out. Another example is for chatbots. All the different messages you're sending out, it's getting fed into some crazy AI ML stuff and doing analysis on it. And that's leading to the actual responses you get from the chatbot. So again, we see some sort of logic or some sort of things happening to the actual data being passed around. And we dug into this quite a bit, and we found there's actually quite a few different categories out there. So there's message transformation, and that's where the actual data in the message is being changed. Then there's message enrichment, and that's where data is being added to the messages. And then there's like message filtering and chatbots, which we talked about. And then also a lot of times messages are fed into some sort of analysis, or they're used to trigger alerts and notifications. And so in all these cases, you're kind of moving away from just sending the raw data between users, and you're doing something else in the middle of it. And so this kind of need or pattern, this is recognized by PubNub and Ably. And they actually have some interesting quotes where PubNub says, you see everyone publishing down to their servers, doing a small bit of processing, and then publishing the message right back out. It doesn't make sense. And Ably has a similar quote where they say, a common requirement in real-time messaging applications is to be able to insert some business logic into a message processing pipeline. And so we thought it was interesting, and it kind of makes sense why this pain point or need was happening, where people were using these third-party services. So they were separating out the real-time infrastructure from their application infrastructure. But if they needed to do very simple different changes to the data in transit, then all of a sudden they would have to send everything to their own servers, and that's tightly coupling it. And then they'd have to go right back into the issues of scaling their own services to meet the needs of the real-time services. And you kind of right back into that tightly coupled system. And so interestingly, both PubNub and Ably, after they recognized it, they kind of came up with different solutions. So PubNub came up with PubNub functions, and these are serverless functions that are actually built and deployed inside the PubNub dashboard. And then Ably took a different approach where you can use a third-party serverless function provider like AWS Lambda, and then that'll integrate into your Ably pipeline. And we love Pusher, and we've dug around and we haven't found an easy direct drop-in for this at this time. But we found it very interesting that these two, PubNub and Ably, did recognize this problem, but they solved the problem in very different ways. So we thought there was something interesting there. And so we kind of looked into it a little further, and we tried to map out what the current landscape of options was. And so if you want to build real-time features and you want to add them to your applications, you have three options. You can either use a third-party service, you could use an open source solution, or you could do it yourself. And so it really depends on what you're prioritizing. So if you want something that's easy to set up, then third-party services are by far the easiest. So that's the PubNubs, the Ablys, and the Pushers of the world. They work really easily, and you can get up and running very quickly. Now, if you want complete control over your data and your infrastructure, then it gets a little trickier. So there's definitely open source solutions out there. You could always do it yourself. So it just depends on what you're optimizing for. And then probably the most interesting one we thought was, if you've recognized this need for real-time middleware, then it gets a little tricky because not all the third-party services support this, and the ones that do support it in different ways. And then you could always do it yourself, but that's a pretty big undertaking. And then at the time that we looked at this, there were no open source solutions. So there was no open source real-time infrastructure solution that supported real-time middleware out of the box. And that's actually what led us to building Ekko. And with that, I'll pass.
Thanks, Will. I'm Drew, and I'm going to talk a little bit about what Ekko is, how it works, and give a little demo. So Ekko is an open source framework, and you can use it to deploy your own real-time infrastructure with that real-time middleware. And there are 4 main parts to Ekko. So the first is the Ekko server, and that's what manages the real-time messages for your applications. Next is Ekko functions, and those are what provide that real-time middleware for in-transit message processing. And then we have the Ekko CLI, which makes it easy to manage Ekko functions and spin up that Ekko infrastructure and tear it down. And the last part is the Ekko client, and this enables you to build real-time applications on top of the Ekko server. And because Ekko is open source and self-deployable, you have complete control over this infrastructure. You can customize it to your needs, and you don't have to rely on a third party to manage your real-time data. So that's what Ekko is, and we're going to try it out and spin up some infrastructure with our CLI tool. So the Ekko CLI tool provides us with several commands that we can use. You can add a help flag to the end of a command to see its documentation. And here we'll run Ekko init, and we'll spin up a new infrastructure. So the CLI gets our AWS credentials, and it uses those along with AWS Cloud Development Kit to spin up an Ekko infrastructure in our AWS environment. So this normally takes 10 or 15 minutes, but we've sped it up here. And it'll also create an Ekko directory in our current working directory. And it's worth noting that you can tear down your Ekko infrastructure in a similar way using the Ekko teardown command. So we've spun up our infrastructure here, and let's go look at a diagram and see what it looks like. So this is our Ekko infrastructure. You can see the Ekko server on the top right. And this is basically a node application deployed in a container to AWS Elastic Container Service. On the left side, there's an application load balancer, and this distributes the WebSocket connections to our Ekko server. On the bottom, we have an S3 bucket and an Elasticast instance, and we'll learn a little more about the role that those play later. For now, what's important to know is that it's this Ekko server that's managing the real-time messages for our applications. So let's set up a real-time application now that uses the Ekko server to manage the real-time messages. So recall that when we ran Ekko init, it created an Ekko directory in our current working directory. In there, we have Ekko apps and Ekko functions, and we'll look at Ekko functions later. Within Ekko apps, we have a few demo applications, and these are designed to help a developer become familiar with building an application on top of Ekko. So we'll be using the chat demo application here. And in there, we have a basic HTML file. And this HTML file runs a couple of scripts. The first is our Ekko client, which is stored on a CDN. And then the other is this script.js. So in this script, we're creating a new Ekko client instance. And this will allow our chat demo application to connect to that Ekko server that we just deployed. So the Ekko client instance takes a handful of parameters, an app name, a host, a JSON web token, and a UUID. So we've set our app name here to chat demo, and we'll generate the host and JSON web token values with our CLI tool. And then the UUID is optional, so no, we're not going to worry about it here. So back in our CLI tool, we can generate those host and JSON web token values. And we'll do that by running the Ekko JWT command. And we'll pass in the name of our application as the argument. So we get a few values here. And the first is the Ekko server endpoint. And we'll paste that in here. This is the endpoint of the server that we just deployed, which will allow the Ekko client to communicate with the Ekko server and send it real-time messages. So the next value that was output is the user JSON web token. And we'll paste that in as well. And this is the value used by the Ekko server to verify that this is indeed a valid Ekko client. And the last value is an admin token. And this is for an application server that gives it special capabilities to subscribe to a special admin channel and get status events. And we don't need that functionality here, so we won't use it. So we've got our chat demo set up, and we've seen that we can use the Ekko client to communicate with the Ekko server. So now let's go test it out. So to do so, we'll open our HTML file in 2 different browsers. And we'll simulate 2 different clients in this way. They're both subscribed to 4 channels you see on the top: boring, angry, backwards, and robot. And when one client publishes a message, it's sent out to our Ekko server, which then emits that message back out to all subscribed clients. So in this case, both clients are sending and receiving the messages. And so now let's go look at our Ekko infrastructure and see what it looks like with these clients connected to it. So you can see that we now have these 2 Ekko clients connected to our Ekko server. And when one client publishes a message out on a certain channel, it goes to our Ekko server, which then emits that message back out to all subscribed clients. So we've seen how an application can use the Ekko server to manage real-time messages. And now let's go ahead and deploy some real-time middleware to process these messages in transit. So if we go back to our chat demo app and we switch to the angry channel, we'll type a message in here. And when we publish it, we expect it to be transformed, capitalized with exclamation points added. But we can see that that's not happening. And so the reason is because in order to process our messages in transit, we need to deploy Ekko functions. So recall that this Ekko functions directory was created. And in it, we have some demo Ekko functions that are designed to go along with our demo apps and help a developer become familiar with how this real-time middleware works. So we're going to use the demo angry function here. And you can see that each function has a specific file structure and format. And that's so it can be deployed to AWS Lambda. So this function in particular, it takes the message payload, capitalizes the text, and adds a few exclamation points. So now that we've seen how these functions work and how they're set up, we're going to use our CLI tool to deploy them. So with our CLI tool, we can change to the Ekko functions directory, and we can check the status of our functions. And we see that they haven't been deployed. So we can run the deploy command to do so. And what this is doing is deploying these functions to AWS Lambda, where they can run alongside our Ekko server. So we'll run the status command again here. And we see that all those functions have been deployed. So there's one more thing we have to do. We have to run updateassociations.json. And what this does is lets the server know which functions are associated with which channels. And we'll talk a little bit more about that later. So back in our chat demo, we'll see if these deployed Ekko functions work. And they do. So now our messages are being processed in transit. It's important to note that we didn't have to refresh the client, or the browser rather. We didn't have to update any client-side code, and we didn't have to update any server-side code. Instead, we're using these Ekko functions that are on our local machine and deploying them to AWS Lambda, where the message processing is done. So the benefits to implementing the real-time middleware in this way are many, and we'll go into some of those later. But for now, it's apparent that this process makes it really easy to create Ekko functions, deploy them, update, and destroy them with our CLI tool. So we'll go ahead now and take one last look at the Ekko infrastructure and see what it looks like with that middleware. So we can see on the right our Ekko functions deployed to AWS Lambda. And when we send a message on the angry channel, it gets sent by the server to the angry Lambda for processing. And the same happens to the backwards channel and the robot channel. So the server knows which Lambdas are associated with which channels using that associations.json file. So that's pretty much what Ekko is and how it works. And now I'll turn it over to Alex, and he's going to talk about some of the engineering challenges that we faced while building Ekko.
Thanks, Drew. So the engineering challenges we faced while building Ekko fell into three broad categories. The first was how to implement Ekko functions. So that's our real-time middleware, and specifically choosing the technology that we were going to use. The second challenge was how to manage the data for linking specific Ekko functions with real-time messages. And the last was how to make sure that Ekko could scale up as load and demand increased. So let's start with the first engineering challenge, implementing Ekko functions. As was mentioned a few times above, we chose to use serverless functions to handle the load. And I'm not going to go into all of the detail on here, and I'm sure many of you are familiar with the concept and even maybe the implementation of serverless functions. But the core reason why we chose this was their flexibility, their ease of deployment. So obviously that had implications for us being able to implement the functions via the CLI tool. And of course, the infrastructure side of things, which I'll talk a bit about later, in terms of their being able to handle bursty traffic. So imagine, again, we have a chat app that's using the Ekko server and filtering out profanity from all of its messages. And we also have a geolocation-based app that needs to hydrate real-time messages with directions obtained from the Google Maps API. These two apps are both routing messages through the Ekko server, but their needs are unrelated, and they have bursty traffic at different times, we could say. Now, if we use serverless functions as our real-time middleware, we can scale the profanity filtering up without affecting the directions processing and vice versa. Serverless functions also provide flexibility. They can be reused across multiple apps, and when functions are added or updated, the rest of the real-time service is not affected. But let's go back to our use case that Will talked about earlier, which is many publishers and many subscribers needing to process messages in transit on demand without any interdependency or need to keep track of state. Our goal was to provide a flexible framework to accommodate changing business needs. And for these reasons, we thought serverless functions were a good fit for our real-time middleware. And as Will mentioned before, this also happens to be the way that Ably and PubNub both handle message processing in their services. Now let's move on to the second engineering challenge, how to manage the Ekko functions. Once we had determined where our real-time middleware was going to live, we needed to figure out how to manage it, specifically linking middleware with real-time messages. Since clients publish and subscribe to channels, it made sense to link specific channels with specific Ekko functions. So if you're making the chat app that uses a profanity filter, you can create a channel and have all messages being published to that channel get processed through the profanity filter. All subscribers to that channel will receive the processed message. We decided on using just a simple JSON file to store those channel middleware associations. And here is a sample of that associations.json file that's being used to store the associations. It's organized by application, as you can see. Those applications correspond to the demo applications that you get on a baseline install of Ekko. Each application has an array of channels, and each of those channels contain an array of Ekko functions to be used for that channel. Ekko will process the message using all of the specified Ekko functions in order before returning the processed message to subscribers. And when it came to making that file available to the cloud deployed service, the JSON file lives on an S3 bucket, which is an AWS cloud storage service. The developer is responsible for manually updating it locally and then updating it with the Ekko CLI tool. We also want to be able to update the Ekko server directly at the same time that we update the new JSON file to the S3 bucket. This involves sending a basic put request to the Ekko server with the JSON file as the payload. This is all handled as part of the CLI tool and happens automatically when the developer uses the Ekko update command. The last of the engineering challenges we want to mention relates to how we set up Ekko to scale horizontally. We wanted Ekko to be able to scale up and down as needed, and of course some of this was achieved by simply choosing the appropriate infrastructure and policies on AWS. The main part of Ekko that needed to be able to scale were the Ekko servers. We needed to be able to support a flexible number of users connecting to the real-time service, as well as an increased volume of messages being published. In order to be able to scale flexibly, a pretty attractive option for horizontal scaling was to package up our server application as a Docker container and then use AWS's Fargate service to scale those server tasks up and down according to how taxed the particular task instance became. Now, Fargate scales according to rules that take into account how much CPU and memory each container instance is using. It's not always completely transparent to use, but it did handle our core problem that we were trying to solve of wanting to horizontally scale our Ekko server functionality. There were some other complexities to actually making this happen in practice, but this is the general approach that we took. And with this infrastructure set up, we did some load testing using artillery.io to validate some of our main use cases. Our first test scenario was that we wanted to make sure we were able to sustain reasonably high volumes of messages published through the Ekko server. To this end, we tested and learned that Ekko is able to sustain 50,000 messages sent per minute. Each of those messages is also in turn transformed by Lambda functions. That's our serverless middleware. For our test, this amounted to a total of 500,000 messages and Lambda function invocations sent over the course of 10 minutes. During the test, AWS's Elastic Container Service spun up 2 additional Ekko server containers to deal with this load. For the second test scenario, we wanted to make sure that we were able to support many subscribers receiving messages. Ekko is able to sustain 600,000 messages received per minute published to a single channel. We were pretty happy with these numbers, and actually these loads didn't max out our server capacities or cause failures. So we probably could have increased the load even further, but it didn't seem like our use cases demanded that. And that's Ekko, an open source framework allowing developers to easily add real-time infrastructure and in-transit message processing to web applications. And by this point, I hope we have shown you how flexible Ekko is to work with. The possibilities available to you are many, as you can see from some of the examples above. The combination of a real-time server with serverless functions as a kind of middleware for in-transit processing of messages offers a rich palette of options. We look forward to hearing what you build with Ekko. You can test drive our code and demo applications by visiting our GitHub repo, and our case study is available to read on our website, along with a fully hosted version of our chat demo app ready for you to try out even right now live. And with that, we welcome any questions you might have.